Video, we're going to be working on a problem which relates to Monte Carlo simulation. Using a Monte Carlo simulation, you aim to determine the value at risk for a portfolio allocated 75% to ASX 200 and 25% to VGB, Vanguard Australian Government Bond Index, with a total investment capital of 200,000 over a period of 30 days from 4th of April 2023 to 4th of April 2024. The ASX 200 expected return is 13.2% and VGB expected return is 3.98% with a 95% confidence interval. To calculate the value at risk, in Excel we require daily price data. Here we have two ETFs, ASX 200 representing the equity stock part of our portfolio and VGB from 4th of April 2023 to 4th of April 2024. In column F, the closing prices for VGB are listed. Daily returns for both ETFs are calculated in columns D and G by subtracting the previous day's price from the next day's price, then dividing by the previous day's price. Make sure to drag the formula down the column so that it is applied for every daily price. We do the same calculations for VGB as we did for ASX 200, thus showing us the daily return on each stock and bond respectively. We will now find the expected returns and standard deviations. As per the question, the ASX 200 expected return has around 13.2%. For the standard deviation, we'll use the Excel formula stddev.s applied to the daily returns for the previous year, then annualize it by the square root of 252. Here you can see me going back on the sheet and highlighting the daily returns for the ASX. Clicking enter will get the answer. We'll do the same thing for VGB, where the expected return is 3.98%, and we'll find its annualized standard deviation. Here you can see me highlighting the data returns. Then I'll insert the 252 trading days to the power of 0.5 to get the square root of the answer. And this will give us our result. Now calculating the covariance between the ASX 200 and the total bond market using the Excel formula covariance.s. This result will be multiplied by 252, as that's how many days of trading there are to obtain the annual covariance of the returns. So I'll go back to the other data sheet, and then I'll highlight both columns, D and G, and in the 252 trading days. That is 0.117.94%. We need to calculate the portfolio variance with our portfolio value at $200,000, with 75% allocated to the stock market, ASX 200, and 25% to the bond market, VGB. We proceed to calculate the portfolio variance using a two-asset formula to find the portfolio variance. We first click on the 75%, which was told in the question. Then we've got a square root times by the standard deviation of the ASX daily prices, which we calculated, squaring it as well, plus the weight of VGB, which is 25%, squaring it as well, times by the standard deviation, squaring that as well, which we can see me clicking here, plus 2 times the weight of the first ASX 200. Oops, let me try that again. The 75% of the ASX 200 times by the weight of the VGB, which is 25%, times by the covariance, which we calculated just before. And that is our answer. To find the portfolio standard deviation, we take the square root of the portfolio variance. To calculate the value at risk, we first need to calculate the expected return. To find this, we first select the total value of the portfolio, which is 200,000, times by, and then putting in brackets the expected return for the ASX 200, times by the weight of the ASX 200, then closing the brackets, then plussing the expected return for VGB, which is 3.98%, times by the weight of VGB, which is 25%, times by the days of the trading period, which is 30 days, over a total amount of trading days, which is 252 trading days. $2,594 shows us the expected return that we are supposed to make in the period of 30 days. So with the Monte Carlo simulation, we are actually going to come up with about 10,000 different simulations. And so we're going to grab a random z-scores for each scenario and assuming the normal distribution. So to do that, we'll say equals norm.s.inv. Then this grabs us a random z-score. And we need to put in a rand function to make it a normally random distribution. So you'll see when I hit Fn on my keyboard, it just keeps recalculating a different random z-score based on a normal random distribution. Then we'll have to calculate a scenario bar based on this z-score right here. I put the formula for VAR down here, which we'll say is equal to the expected minus the portfolio value multiplied by the portfolio standard deviation multiplied by the z-score and multiplied by the number of days in the period divided by 252 trading days. Then we put in the exponent of 0.5 because we need to take the square root of that time period. Now we need to do the actual simulation for the Monte Carlo simulation. We know that confidence interval is 0.95 as it was stated in the question. And now we need to do the simulations. To do the simulations, we'll create a new column here and start doing the simulations. Oh, before I forget, instead of just dragging it down like this to create 10,000, and it'll take a long time, we can just, let me do like this, highlight the whole column and go here, click series, click columns, and go to stop values, which is 10,000. And this will create the 10,000 numbers for us without manually doing it. I'll quickly make this a little bit neater. Okay. So in this box here, we click on the value at risk and click enter. And to do the simulation, we highlight these two boxes, go to data, click on what if analysis, click on data table, and then in the input column input cell, you can just click anywhere, and this will trick the what if analysis to make those 10,000 generations. Now, to get the actual answer for the Monte Carlo value at risk, we go here in the box that I've made and type in percentile dot inc. Then we go from number 1 all the way to the bottom, which you can do by pressing Control Shift, then the down arrow, then pressing comma, and then we drag all the way up. 1 minus the confidence interval. So we know that this is our range that we actually want to find, which is right now it is $5,353,000. To make it a little bit easier to see, we can actually make this into a chart so we can constantly see the changes every single time we do a new simulation. So if we go to insert while highlighting the column and click on histogram, and then I'll move this up. See that this is approximately a standard normal distribution. As you see, as I continue to keep running this, I'll change shapes and sizes a bit. Then you'll see that always around the Monte Carlo bar of around 54,000. So we find that the bottom 5th percentile of this distribution is going to be around this bar here. Yeah. This bar here. And this is our 5th percentile. This is where our 95% confidence interval bar is in a 30-day period. But if we change this, it will constantly keep moving up and down as we run the simulations. Therefore, it can be seen that the value at risk for this using a Monte Carlo simulation is about $53,000 to $54,000.